This is Lecture 5A for Calculus 1, Introduction to Integral Calculus. This semester in Calculus 1 has really two sections to it. One is differential calculus, that involves taking the derivative, and the second is integral calculus, which involves integration. These two parts do fit together. The way they fit together is established in the fundamental theorem of calculus. But before looking at that theorem and working through all that, it helps if you know a few definitions and if you get an overview. So that's what this lecture is, an overview of integral calculus. Anytime in math we do one thing, we try to undo it or figure out if we can get back out of it. It's kind of normal in life. If you take the derivative, or that's called differentiation, of course, then the inverse is called antidifferentiation. That makes pretty good sense. But we're going to have different names for the functions involved. If we call one function the derivative, and let's call the other function the primitive. So we have the derivative and the primitive, and they're related in the following way. By differentiation, you take the primitive and turn it into the derivative. By antidifferentiation, you take the derivative and try to find the primitive. So they're inverses of each other, but the names we call one function is the derivative. What it came from is called the primitive. Taking the derivative you pretty much understand already. It's fairly straightforward. But there are two big problems with antidifferentiation, with looking for this primitive. First one is that sometimes the primitive is very obscure, very hard to find, and sometimes it cannot even be found at all. The second is that the primitive can never really be totally specified, since differentiation caused loss of information. So here are these two problems with taking the antiderivative or with finding the primitive. Those are equivalent statements. First, the primitive can be very hard to find if it can be found at all. Second, even when you do find it, you can't totally specify it because differentiation caused loss of some information. So we have solutions to these problems. The first is a solution to hard to find primitives. Well, first, many antiderivatives, or primitives as they're called, either name is equivalent. Not all of these are obscure, and many are very obvious. Also, people have been working on looking for them for a long time, and every time they find them, they publish them and put them in handbooks. So you can look in the back of the textbook, or there's many other books, of course, on the internet. Some of these computer programs contain lists of them. Anyway, you can find them. People work on them and publish them, so there's a whole bunch that have already been found and established. There are several tricks. You'll learn those later in this chapter. One's called substitution, which is the inverse of the chain rule, in a sense. And then, if all that fails, there are numerical techniques which will allow you to approximate the primitive. Now here's our second problem. It's loss of information, so I think we have to specify what that means. I can't seem to get the highlighter here. No. There we go. Okay. Here's what happens. When you take the derivative of a constant, the result is 0. So if the function had a constant associated with it, that information is obliterated by taking the derivative. So when I look at the derivative of 0, I have no way of knowing what constant it came from. This is like multiplying by 0. If I multiply by 0, all history of what I multiplied is gone. Say you have, for differentiation, say you have this function, 2x squared plus 125. If you take the derivative of it, its derivative is 4x. Now, what functions have the derivative 4x? Well, 2x squared does, 2x minus 25 does, 2x squared plus 125 does. In fact, all kind of functions have it that have the form 2x squared plus a constant. This is what it means that taking the derivative caused loss of information. So all that I can really say is that the primitive has this form 2x squared plus c, where c is some constant. These primitives, as you can see, make up a family of functions. We've had family of functions before too, like with orthogonal trajectories, or looking at the a family of functions that were exponentials, or in this case, this would be a parabola, all shifted by c. So we're used to that. But that's what the primitive is. All I can say is that the primitive has this form, 2x squared, which will give me the derivative 4x, plus c. And the c could be any constant. Its value could be 0, or it could be minus 25, 125. It doesn't matter. If you know the value of c, then you will identify one member out of that family. There's special notation for taking the antiderivative, and it's a shorthand for saying these words. We could say the function 2x squared plus c is a primitive of 4x. That's a lot of words. Or we can use this notation. Here's the notation right here. It starts off with this elongated s. That's the integral sign. Okay. After that, you put the function that you want to find the primitive for, so the 4x, that's. After that, there's a dx. You'll understand what d is in a few minutes in another context, but the x specifies the variable of integration. It's really what's called a dummy variable because it sort of gets combined, but in this case, it's not. There could be other variables around, but this means I want to find the function that by taking the derivative with respect to x, I would get 4x. And then here's the answer out here. C now has a name. It's called the constant of integration. That's its name. And this is called the indefinite integral. Indefinite. Now we're going to switch gears, so to speak, and talk about something that is seemingly unrelated, and that's called Riemann integration. This is a numerical technique for computing the area between a curve and the x-axis. So think about the graph of a continuous function and look at it between x equal a and x equal b. And assume that it's positive, so you don't have any, we'll just assume it's positive for now. That's good enough. Now we create, for this Riemann integration, this numerical technique, we create what's called a tagged partition. A partition is like a mesh, right? That means we subdivide this interval AB. We break it up into, say, if we broke it up into 100 small intervals, each one would be this big. Delta x would be b minus a over 100. So just say you have the function and it goes from 4 to 10. So if you broke it up into 100 little subintervals, that would be 10 minus 4 would be 6, divided by 100 would be, they would be 0.06 in width. Out of these little subdivisions, you create a bunch of rectangles. You create the rectangle by tagging the function in each little section with one value. We'll call it f star. Okay, x star. X star is a value in the little subinterval, and you pick out a value for the function. Then you draw a straight line, you call that, then you make a little rectangle. Here's an example. The red line is the function. It's going from 0 to 4. For purposes of discussion, I broke it up into 4 subintervals. Between 3 and 4, 2 and 3, 1 and 2, and 0 and 1. I made them all the same size. Okay, that was my partition along the x-axis. Then I go up here and I tag this little section here with the value of the function. In this case, I'm tagging it with the value of the function on the right-hand side of the little subinterval. And with that value, I create a rectangle. Okay. Then I go to this one and I tag it with the value of the function here, which is right here, with that star. Okay, and that creates for me another rectangle. It's an approximation of the function. All right, it's crude, but this is a start. So now here's my green rectangle, and I tag that one with the value of the function again at the right-hand side of the little interval, and here's another one, a blue one. Okay, so I made all these little rectangles. I didn't have to tag them with values at the right-hand side. I could have done it in the left-hand side or in the middle. Here's the same function and the same partition, but now I tag them with a value of the function right in the middle. So here are all my little triangles. And what I'm trying to do is figure out the area between the red curve and the x-axis. So I want to go here and calculate all this area in here. Whoops, I can't draw it because I can only draw squares. So I want to get all the area underneath it, but I don't know how to do it, so I break it up into little intervals. I pick either the midpoint or the right-hand side or the left-hand side for my function evaluation, draw little rectangles. Obviously, if I keep subdividing this smaller and smaller and smaller and smaller, it could eventually be very close. The area of all these little rectangles could add up to the area in the limit, to the area under the curve. So we're doing the same thing here that we've always done. We wanted to find something for curves in general, not just straight lines. We only know how to do things for certain geometries. We know how to take the area of rectangles. So we approximate the curve as though it were a bunch of little rectangles and add up their areas. So we use the tool we know how to do. Then we refine the tool by making smaller and smaller rectangles. We can only make them so small. So then at that point we take the limit and we jump over with the limit. We finesse the answer out of it and we get the area underneath that curve. That's Riemann integration. So here we go. The area of each little rectangle is the value of the function. That's the height of the rectangle times delta x, which is the width or the base of the rectangle. Delta x is just that little, the width of each little subinterval after I partitioned the x-axis. So the area under the curve, I'm just going to call it sum now. I have to sum up all over all those little ones. Say I broke it into 100 pieces, so I'd have to go over 100 little rectangles. And the fxi would be the value of the function inside the little rectangle. So you see how you'd make those rectangles grow or get smaller depending on whether the curve was very far from the x-axis for a while or very close. Usually a finer partition, that means a smaller and smaller mesh, would give better agreement between the Riemann sum and the actual area under the curve. And the idea is that as we refine it, we cannot take, we always have a little bit of an area. We're going to have a little bit of a gap because we're not going to be following exactly along the curve. But in the limit, we say that the limit as, usually I use n, but this time I used I, goes to infinity. And I is the value up here. As the number of subintervals, that means the number of intervals in the partition, as that approaches infinity, then the sum of all these little rectangles added up approaches the area, is equal to the area under the curve. So I'm going to go over it once more. We don't know how to compute the area under the curve. We do know how to compute the area of rectangles. So we approximate the function, approximate the curve by rectangles, because we know how to take their areas. Then we refine this idea by taking smaller and smaller, or thinner and thinner rectangles. We can only get them so thin, but we see that they're approaching something, so we can take the limit. The limit allows us to go over from rectangles to the area of the curve. Just like with the antiderivative, we have notation for this. It's going to look familiar, and at some point in a couple of slides you'll see it all come together. Okay, I'm going to say area that's the area between the curve and the x-axis. Then I'm going to use that integral sign, the elongated s, meaning summing things up, and I'm summing up little rectangles. So that's what it means. Then at the a and the b are called the limits of integration. Those are the extreme points on the x-axis where I'm trying to compute the area. So a is the lower limit and b is the upper limit. They don't have to be ordered like this, and you'll see some rules on that in the future. Okay, so those are the limits of integration. A is the lower limit, b is the upper limit. After that, I write the name of the function whose graph I'm trying to integrate, or trying to calculate the area under, and then dx. And now you understand x, of course, is the independent variable, but now you understand what the d is. When we had the little partition, let me go back and show you. Here, I can show you two slides at once. When we had the discrete sum, we had f evaluated at x, all right, in the intervals, and here was the width of each little subinterval. Delta, the Greek capital delta, usually in mathematics and in other fields too, represents change, and it could mean a fairly big change. So as we let that change get smaller and smaller, we go from using a capital letter to using a little letter, and that's what the d is. dx. It's related to the delta x. Here you see the function, and instead of counting all those, all we have to do is say we're going from a to b in with a partition so fine that is actually the limit of a discrete partition, and we call the answer the area. So in the limit, as the number of subintervals in the partition goes to infinity, this Riemann sum here in the limit becomes what is called the definite integral. What does it make it definite? It's definite because you have I'll show you what makes it definite. This is what makes it definite, the a and the b. That makes it definite. The indefinite integral that we were using to represent the antiderivative did not have an a and b on it. It just had the sign, the integral sign. That's called the indefinite integral. When you put the little a and b, when you put the limits on the sign, that's called the definite integral. I want to mention something here that you can see later. Actually, under failures to integrate, I believe, is where I talk a little bit more about this. This was Riemann integration. There's another thing called Lebeque integration. I wrote here how to pronounce it, Lebeque. All right. That's a numerical technique similar to Riemann sums, except that when you generate the partition, you do it along the y-axis instead of along the x-axis. Then the long axis of the rectangles is horizontal. And this works better for some graphs. The idea is the same. In fact, some things can be integrated by Lebeque integration that could not be integrated by Riemann integration. Okay, now we're going to take this one little step further. Right. And we're going to develop two ideas that will give intuition. And I think this is reasonable. Okay, I'm going to go on a road trip. On this trip, I'm going to go 60 miles an hour for 4 hours without stopping and keep that speed. I guess I'll put on cruise control. Then for 30 minutes, I go 85 miles an hour for some reason. I don't know why. I guess I entered Montana. And then I go and slow down and go 37.5 miles per hour for 6 hours. How far did I go? Okay. How would you find out how far I went? You would take the velocities and multiply by the time. I went 60 miles an hour for 4 hours, 85 miles an hour for half an hour, 37.5 miles an hour for 6 hours, and I would come up with 507.5 miles that I drove. Okay. I'm going to equate this to Riemann integration now. I'm going to do that by making a graph of the velocity. So this is velocity, here's 60. So I went 60 miles an hour for 4 hours. I'm sorry that this is a little bit hard to read at the scale on the internet, perhaps. Then I went 80 miles an hour. That's this one right here. I went 80 miles an hour for half an hour. Then I slowed down, and this big yellow square, I went 35 miles an hour for however long I went that. Can't remember. Right. If I take 60 miles per hour and multiply by 4, I have developed, right in there, I've developed the area. Well, I could put it inside of it since I can't draw an arrow with it. That is the area under the velocity graph. And here, by multiplying the 80 miles an hour by half an hour, I've got the area under that little piece of the velocity. I have created a Riemann, I've taken a Riemann integral of this velocity curve. It wasn't a curve, it was straight lines. So in a sense, it's, it's fairly easy. But here's this is the concept. I graphed the velocity with respect to time. When I multiply the velocity by time, what I really get, if you just look at it graphically, is I get the area under the curve. Right, so I hope that concept is clear. I've really gotten the area under the curve, and we know what that's called. That's called Riemann integration. Of course, we have a use for it now. It's not just an area. We say now when I do that, I get the number of miles that I drove. But look at this. So first I'm going to use the notation for Riemann integration because we know what it is. I'm integrating the velocity. Let me go slower. I'm integrating the velocity with respect to time. I start at time 0 and I go to time 10.5 or 10.5 hours later. And when I did that, I got the distance traveled. On the other hand, you would say there's an easier way to calculate the distance traveled. Say you started at mile marker 104, and when you stopped you were at mile marker 611.5, if there was such a mile marker. What was your distance traveled? Subtract them and you would find out you would get 507.5. So there was two ways to calculate the distance traveled. One was take the velocity and multiply by time. The other was take the two displacements and subtract them. All right? So I took the location at time 0, which was 104, the location at 10.4 hours later, 10.5 hours later, which was 611.5. I subtracted them and got the distance traveled. There was two ways to get the distance traveled. And there's a function, of course, s represents the distance traveled, or the distance. And so I took s, evaluated at 10.5, and subtracted s, evaluated at 0, and got my answer. These are two equivalent ways, but here is the whole trick. So because these are two equivalent ways, I'm going to equate them. Here is how I took that, found that area under the curve by multiplying velocity times time and summing up, integrating. And here is how I found the same answer by subtracting the displacements. Displacement at 10.5 and then subtracting the displacement at 0 from that. The trick is, what is the relationship between velocity and s, between the v and the s? Velocity is the derivative of s. In other words, s is the primitive of velocity. So what this is saying is if I want the integral, I want the area under a curve, okay, from some starting point to some ending point, I can either take a bunch of little rectangles and try to add them all up, or I can find the primitive evaluated at 10.5 and subtract from it the primitive at 0. So now you see how the integral and the derivative are combined. They're combined through this primitive. So what you're doing, integration is really taking the antiderivative. So here's our result again. And I'm going to say it again so hopefully it's clear. If I want to find the distance traveled, or if I want to find the area under the velocity curve, I can do all the little Riemann sums and take the limit. Or I can go off find the primitive and then subtract the values of the primitive at the endpoints. So in general, if f, capital F, is a primitive of little f, then if I want to integrate from a to b, f of t dt, and it doesn't matter what the, okay, just leave it like that. Here's the function, and I want to integrate it from a to b. I go and find the antiderivative, which is f, evaluated at the upper endpoint, subtract from it the primitive evaluated at the lower endpoint, at the lower limit of integration. I'm going to repeat this whole idea with another example so that hopefully it's clear. Say you had stock losses over 28 days. You lost $6 a day for 15 days. Then you lost $3 a day for 10 days. Then you lost a whooping $20 a day for 3 days. Oh boy. Okay, how much did you lose? All right. Here are the stock losses here. This was the blue line, this heavy blue line right here. A dark blue curve. That was when you were losing $6 a day for 15 days. This lighter kind of teal colored one, you were losing $3 a day, but you did that for 10 days. Then, in this big yellow one, you lost $20 a day for 3 days. if you wanted to know how much money you lost, you would be computing the area between this curve and the x-axis. Of course, this is negative. Now, a lot of times we talk about area with integrals, and then the idea comes up, can an area be negative? We use the word area, but it's a signed area. It has sign associated with this. In this case, you're going to come up with a negative number, because that would be multiplying, minus 6, not minus 16 times 15, minus 3 times 10, minus 20 times 3. 50, 30, 90. Okay, this should have been 6 instead of 16 right here, but that's okay. The idea is here. You take your losses, multiply it by the number of days you lost, and what you're doing is it's a Riemann sum. I don't have to refine it any because the function was so linear. But that's one way to calculate those stock losses. I know that is the definite integral. It's the integral of, let dv by dt mean the rate at which my stocks are losing value. And I'm integrating between 0 and 28. And I found that I lost $330. There's another way. I could look at the value of my stock at 0, the value of my stock 28 days later, subtract the two, and get the same answer. So here's a statement of this. If I want to, so obviously v and dv by dt, for dv by dt, v is its primitive. V is the primitive of dv by dt. Okay, so I'm integrating this function from day 0 to day 28. I can do it either with a bunch of little triangles or little rectangles and add them all up, or I could take the primitive, which is b, get its value at day 28, the upper limit of integration, and subtract from it the value at the lower limit of integration, and that will give me the same answer. So now we're going to apply this idea, but have no application associated with it. Let's just say we have a parabola, and the parabola is 12x squared plus 235. And we want to find the area between the parabola and the x-axis between x equal minus 7 and x equals some strange number, 0.3357. Okay, how can I do this? Well, let me make a statement of what I'm doing. This is my function. I'm trying to integrate it because I want to find the area between it and the x-axis. So I'm looking with respect to the x variable. My starting point is minus 7. My ending point is 0.3557. Now the way to do it is to create a little Riemann sum, add it up, try to make more and more little triangles, and work on that. Or you take the antiderivative of the parabola and evaluate it at the endpoints. So I have f is going to be the primitive of the function I'm integrating. What is the primitive of 12x squared plus 35? Well, it would be 12 over 3x cubed plus 235x plus some constant of integration. So I evaluate that function at both endpoints. Here I'm evaluating it at the upper endpoint. So every place there's an x, I have to put this value here times that, and then I have the constant. Then I subtract. I'm doing the same thing. I'm taking this primitive again, and I'm evaluating it at minus 7 and subtracting it. So here's the subtraction. And now here's the minus 7 sitting there. Here's the minus 7 here in place of the x, and the constant of integration. Obviously, you've got plus c and minus c. Those constants vanish. So it does not matter. The constant of integration in this case doesn't matter. It does matter for the statement of the primitive, but as you can see, when you evaluate it in the definite integral, it subtracts off. What we have really is a summary of the fundamental theorem of calculus part 2. There's 2 parts to it. So here's the summary. To find the area, which has physical meaning in some cases, such as the case of velocity and stock market losses, there are 2 methods. 1, construct the Riemann sum and refine the partition and take the limit. Or 2, find the primitive and evaluate the primitive at the endpoints of the interval. Connecting these 2 ideas is attributed to Barrow and to Newton, So very great minds made this connection. If you don't see it immediately, don't feel too hard on yourself. But hopefully this introduction would kind of explain it for you. Okay, now fundamental theorem of calculus part 1 isn't going to seem as, I don't know, it's not quite surprising because we've already been using the notation so much. First, I need to make a comment on notation. When you make, you can let the limit of integration be a letter. For example, I could write this as lower limit, I could call it a, and I could call this t and sort of do things in abstract. But if you have a letter up here as a limit of integration, you cannot use the same letter down here. So if you use the t up there where it's yellow, you can't use the t down here. This is wrong, right? The one in green, the one that's under the integral sign, not in the limit, is called a dummy variable, because when you're done integrating, you're going to substitute a or whatever numbers for that integrals, for that variable. So it doesn't really matter what you do. Typically, if you have t in the limit of integration, you use a different letter like the Greek letter ta in the integral. And these have to match up, but they cannot be the same as the t up there. Okay? Okay, so for the fundamental theorem of calculus part 1, it won't seem so surprising because we've been using the notation and the ideas all the way through, although in a very casual way. We kind of made a connection. So basically you start with this definite integral now to state this fundamental theorem of calculus part 1. You start with the definite integral. The lower limit of integration a, you choose something so that f of a will be 0. For the upper limit of integration b, you replace that by the variable x. So here's what you end up with. I'm integrating from a to x of f of ta d ta, or you could have used t in this case, equals, it would have been f at b, but b is evaluated, but b is x, so you put f of x minus f at a, but f of a was 0, so you don't have to write it. And the fundamental theorem of calculus part 1 states that if you took the derivative of f, capital F, you would end up with little f, which is just a statement that capital F is the primitive of little f. But we already made that connection before. So there you have, that's a little overview of calculus. We're going to do a lecture on finding the primitive, on antidifferentiation, a lecture on Riemann sums, and then another lecture on some of the tricks for finding integrals. In the last lecture in this chapter, I will have just one that is just a proof of the fundamental theorem of calculus. You're not responsible for knowing it, but you need to see it once.